Hi everyone. I'm excited to share with you a lecture today on how to solve nonlinear equations using scipy. And so let's go ahead and launch right in. We're going to do a little bit of discussion here with pencil and paper, and then we'll move over to Spider, and then we'll work do some examples there. So let's start off and talk about systems of nonlinear equations. So that's our first part here. So this is our outline for today. We're going to start out talking about systems of nonlinear equations, and then we'll talk about how to do root finding in those systems using scipy. So it's often the case that we don't just have a single nonlinear equation, but that we actually have multiple coupled nonlinear equations. So this is systems of NLEs, and I just put NLEs because I get sick of writing nonlinear equations over and over again. All right. So for a system, recall that we have multiple equations and multiple unknowns. Okay, and they also need to be coupled. All right, if they're not coupled, that is, if the variables aren't in both equations or in all of the equations, at least somewhat, then you just have a system of independent equations and you can solve them using the techniques we've talked about in previous courses. All right, so let me give you an example of a problem like this. All right, an example would be z equals e to the minus y, and y is equal to 3z minus z squared. Okay, so here we have two equations, two unknowns, 1, 2, all right, and we only have, so the two unknowns are y and z, the two equations are 1 and 2, all right, and they're coupled because we have z in both and y in both, all right, so we can't solve one without solving for the other, all right. So now you might immediately, see a way to decouple them. You might say, oh, I can take this equation and plug it into here and use analytical methods to try and decouple them. But even if you do that, you're going to notice you have an implicit equation. You're able to solve that right away. But we're going to ignore that for now because this is an easy practice example. We can use numerical tools to solve much harder examples than this, but let's use this easy one at the beginning. And I also want to just remind you that we don't know if this set of equations here is going to have one solution, zero solutions, or many solutions, infinite number. We don't know a priori for nonlinear equations. It turns out this one has at least one solution, or I wouldn't have picked it as an example, but I don't remember off the top of my head how many it does have. Okay, so one of the things that we need to do is take something like this and we need to write it in a more standard form. So recall, we want to write this in standard form. Okay, we also call that residual form. Okay, so in the case of a single nonlinear equation, single nonlinear equation, that looked like f of x equals 0. Okay, so we have two equations here, two unknowns. Let's write each of them in what looks like standard form. So that shouldn't be too bad. I'm going to take z minus e to the negative y equals 0. That's some function equals 0. And I have y minus 3z plus z squared equals 0. Okay, that's also in standard form. Okay, and that's useful. I could call this, for instance, f0. I'm going to make it a small 0, f sub 0, and I could call this one f sub 1. Okay, so I have two equations, right? But I'd really like to be able to write this in a way where I can write down a vector f, which I have f0, f1, which would be f0, f1. And I'd like to express that f as a function of a vector x. So I need x, which the components of x would be x0 and x1. I need those to be these variables that I have here. So I'm going to call x0 y and x1 z. Okay, and I'm going to rewrite them then by substituting in x0 and x1. So if I rewrite that, I now have f1 is equal to x1 minus e to the x0, or excuse me, this is, let me start over so I don't confuse us all. This is f0 is equal to z should be x1 minus e to the minus x0. And down here I have f1 is equal to y as x0 minus 3x1 plus x1 squared. Okay, now I've written it in this form. So this is in my component, vector components, vector notation, okay? And when I write it like that, I can then write final standard form of f of x, where both of these are vectors, is equal to 0, where now 0 vector is, of course, the vector with zeros in it. Okay, so we're going to see that that's useful for solving these kinds of problems when you're treating them numerically. All right, let me turn my page here. Okay, so that's just a simple two-equation example. We can write this more generally if we'd like. So for the general case, okay, we get the following. I can write down f0 as a function of x0, x1, all the way to xn minus 1 equals 0. And what I mean by that is I have n minus 1 equations and n minus 1 unknowns. Okay? Or excuse me, not n minus 1. It's n equations and unknowns. Wow, making all sorts of mistakes today. N equations and unknowns. Okay? Because I count from 0 to n minus 1. So f1 is also x0, x1, xn minus 1. And I'm going to have n minus 1 of these equations. So I have fn minus 1, x0, x1, all the way to xn minus 1 equals 0. Okay? And in the end, that looks just the same. I get f of x equals 0, where f is the vector f0, f1, fn minus 1. X is the vector x0, x1, xn minus 1. Okay? And the 0 vector is the vector of zeros. Okay? So that's the standard form. And it's also residual form. Well, why is it the residual form? Well, remember, if I have, since all of these should be 0, if I plug in the x's that I think are the solution, they will give me something that tells me how far away from the actual solution I am, because each of these will have some value. I can calculate a residual, say by taking the norm of the vector of f's, and that will tell me if I am converged or not to my solution yet. Okay, so one last thing we want to say about systems of nonlinear equations. Okay, and this is important. Okay, when we write code, okay, we need to write our functions as vector equations too. So our functions in Python need to be vector equations too. Okay, so I'm going to write a little bit of pseudocode to show that. And whenever you hear the word vector or matrix, right, you should think NumPy array. Okay, that's what you should be thinking. That's what we're going to need to use. So if I wanted to write this guy up here, if I want to rewrite these, how would I define a function to do that? So here we go, pseudocode. Okay, so I need to def f of x, okay, and then I'm going to have some variable here I'm going to call f0, and that's going to equal minus numpy dot exponential of x0, okay, plus x1. Okay, so I'm treating this as an array that's coming into the function, okay, and it has these components x0 and x1. So let's look back up at this one, right? This has minus e to the minus x0 plus x1. That's the same thing here, minus numpy.exponential x0 plus x1, okay? So I'm using this as an array. I'm not doing f of x0, x1, okay? I'm not doing that. That's the wrong way to do it. That would treat each of these as individual values, okay? Not as an array. So I want this to be an array that's coming in, okay? I can do the same thing for f1. So let me remind myself of the equation. It's going to be x0 minus 3 times x1 plus x1 squared. Okay, so that looks similar. Oh man, let's see, 3 times x. That's kind of messy right there, huh? That's supposed to be an x. That didn't help at all. Hard to do things on a computer. Okay, that's a times. Okay, so that should look like this equation, x0, yep, minus 3x1, yep, plus x1 squared, x1 squared. All right, so that's uses the same principle there. Okay, now the last step, okay, is I need to return a value, and I also want to return a vector. Okay, so I want this guy to be a vector. So I'm going to make an array, numpy.array, okay, of the components of the function I'm going to return, f0, f1. Okay, so f is also an array. Okay, there are the components. Okay, so when I return, it's going to return an array. Okay, notice that this isn't a tuple. Okay, so this isn't return f0 comma f1. Okay, not a tuple. Okay, I'm returning a numpy array. Okay, so that's the idea about how to do systems of nonlinear equations. All right, and what we're going to see is that this format of writing using arrays and using this standard format is going to be critical to being able to use scipy's root finding functions. All right, now part 2. Oh, actually, I lied. Before we get to part 2, I want you to do a quick activity, okay? So I want you to do the following, okay? I want you to practice for yourself. This is some practice, okay? Write the following, okay, in vector notation, okay? And write pseudocode. I'll just put PC, okay, to define a function, define a vector function. Okay, so of the following, so I've got cosine a squared plus b squared inside the cosine is equal to 2, and then I have, let's see, log of 3b is equal to minus a squared. Okay, that's supposed to be a b. Okay, all right, so take that and go ahead and pause the video and practice for yourself, and you can look up the solution in the notes online. So I'll just leave that solution in online notes. Okay, And I'll put a link in the description if you're not in my class and you want to look at these online notes. All right, so that's enough for 1. Let me go to 2. Okay, 2 is scipy root finding. Okay, so we are now ready to solve systems of nonlinear equations and single nonlinear equations for that matter using scipy. So in the past we've talked about NumPy, okay, and it has a linear solver in its submodule linalg. Okay, it's in linalg in there, and we're scipy, okay, is a different module. So it's a new module, okay, kind of like NumPy. It's like a sister or a friend, okay, of NumPy. So NumPy is numerical Python, scipy is scientific Python. So that's what that stands for. Sci is scientific, Pi is Python. And the way I kind of think about it is NumPy, for the most part, defines all of the things you need to do numerical calculations like arrays and multiplication and all of the sort of really base level stuff. Okay, scipy defines a lot of the more advanced methods. So this, I sort of view NumPy as the foundation, and then scipy is built on top of it. I didn't give myself enough space, so scipy is right there. Okay, and it has a lot of numerical methods built in. So NumPy has some basic linear algebra functionalities, but actually scipy also has some linear algebra functionalities that are more extensive, and then it has nonlinear and all sorts of other stuff that it can do. Okay, so scipy is your friend. Both of them are your friend, hopefully, so you don't have to write these things yourself. Okay, so you can import the scipy module the same way that we import other modules. You import it as follows with the import command. You do import scipy, okay? But this has many submodules in it, okay? So it has, like I said, it has a linear algebra one, okay? So this has linear algebra, like eigenvectors, okay? We haven't messed around with that, but those are super fun, right? Okay, and the one we're going to talk about today is optimize. Okay, optimize has optimization algorithms. Optimization. It's amazing how spelling is hard. And it has root finding, which is what we care about today. And we will see next time we're going to have a lecture on optimization, and hopefully you'll see from that how root finding and optimization are connected and why they might be organized together. Okay, but what I'm going to, looks like I need a new page. Okay, so when you want to import the submodule, you can do import scipy.optimize. Okay. And then this won't import all of scipy, it'll just import that submodule. And I usually like to put an as opt at the end, without the period, okay? So that I only have to type opt instead of optimize or scipy.optimize whatever when I'm using this module, okay? And the function that we're going to use is called root. All right, so let me write that down. So the function for solving both, okay, this will be for both single and systems of nonlinear equations, okay, is called root. All right, so hopefully that should be relatively easy to remember because we're doing root finding. So here's the syntax of how it's called. Syntax right here. We're going to call x solution is assigned to opt, okay, if you followed my import procedure there, dot root, right? And we're going to give it f, which is our function, comma x guess dot x. Okay, so I'm going to explain what these different parts are. So here I have the module name. Okay, this is the function I care about, right? Root finding. Okay, that's the root finding function. Okay, and then I'll talk about these two in a second, but this is the function I want to solve, function to solve for the roots. Okay, and x guess is an initial guess. Right? Hopefully from our discussion last time of Newton's method, you can understand why it wants an initial guess. All right? So it wants to use what you know to help find the root. All right? And it's going to use an iterative method just like you learn an iterative method. Okay? And then the last thing you have to put is this dot x at the end. Okay? And that's because opt.root returns a dictionary. Okay? So opt.root returns a dictionary. Okay, and we haven't talked a lot about dictionaries, at least in my class. And if you're not familiar with them, you're welcome to look them up. But basically, it's like an array or a tuple that has named pieces. So if you call .x, this is going to give you just the solution part. Okay, so .x is the solution part. So it turns out it'll return a whole bunch of other things, statistics about the solution, how many iterations, etc., you can find out. And so most often you don't care about that, so you just put .x at the end. Okay, so a couple of comments about root, and then we'll look at an example, okay, and then we'll let you have some practice. Okay, so a couple of comments. So the first, okay, is that f needs to be a function, okay, in the programming sense. Okay, so let me show what I mean by that with just a good and a bad example. So here's a good example, okay. A good example would be def f of x colon return x squared. Okay, so this is a function. I've defined a function and it can accept values x squared. Okay, a bad example that won't work with root would be to just define an array f is equal to x squared, or just a single number. All right, so if I write this, what I'm doing is I'm calculating a value f given that I have x. Here I'm defining a relationship between an input and an output. Okay, this is what I want, this is not what I want. Okay, so that's the first thing, a mistake that's commonly made. Right, the second thing is something I told you earlier, but I'm just going to reiterate it to drive it home. Okay, so when solving a system of nonlinear equations, you must define a vector function. Okay, so you must define a vector function. So again, a good example, I'll give a good example and a bad example to make this hopefully crystal clear. Okay, so a good example, I define a function, f of x, and I have f0 is equal to, say, x indexed at 0 multiplied by x indexed at 1. f1 is equal to x indexed at 1 star squared. Okay, that would be some function, x1 times x2, or x0 times x1, x1 squared. All right, and then return numpy array. Okay, f0 comma f1. Okay, that's a good example. Okay, a bad example would be the case where I don't define a vector function, I just define something like this. So def f x comma y, and I return x times y comma y squared. Okay, so this is not a good example. Okay, this is not an array. All right, and this is also not an array. Okay, this is a tuple here. And this is two separate variables. Okay, this is bad. Don't do that. Yes, do that. Okay, so if you do those two things, okay, hopefully you'll be able to use scipy.optimize.root. Okay, so that's all I have for the written out part. I'm going to put a little box here for the activity. So if this is all you're coming for, you can go ahead and close out the video. But I'm going to now move over and do an example. Okay, examples of solving nonlinear equations using opt.root. Okay, that's where I'm going to go next. Okay, so moving over to these examples, I'm going to actually pull my picture down, not because I think I'm special, but just because I think it makes the video less boring when you can see me. Sometimes I gesture, right? So hopefully that helps. And I'm going to move my tablet out of the way, grab my keyboard, and let's zoom in a little bit here. Should have done this before, but let me just zoom in a little. Make this maybe size 16. We'll go a little more. Okay, so this is some reference up here, okay? And notice that I have some references down here to the documentation. I highly recommend that you look at the documentation. We can pull that up just to show what's going on here. If I copy that link and I pull up the documentation, put it over here, get rid of that. Okay, it'll pull up optimize.root, and it tells you all the parameters you need, the things that it returns, things about the methods, references for those papers, okay, where they come from. Great stuff in the documentation. SciPy is awesome. Okay, so what are the steps to solving this here? So the first thing is to import the module, okay, and the second is to make sure that your equation is in residual form. All right, for a single equation, unknown, we know how to do that. Move everything to one side. Then you need to come down here and define a function. So if we're going to solve this quadratic equation, x squared plus x minus 5, then we define the function as follows. Def f of x, return x squared plus x minus 5. Okay, and then we need to set some kind of initial guess. Right, so here I'm just plotting it. Plotting is a great way to find an initial guess if you don't know. Especially for a one-dimensional function like f of x. Okay, so from that, and let me go ahead and maybe I'll just do that right here with while we're in real time, so I can run that. Control Enter. Oh, apparently I didn't run this up here. Import, run that, and you can see I get a plot out, and you can see that it's not going to be at 2, but 2 is a pretty good guess, and you don't need to be that close, right? So that's okay. All right. Then comes the big thing that I need to do. The big new thing is call my solution is assigned to opt.root, where I have the function and then my guess. Okay, and then I can print. This is example 1. Print the residual, and I'm going to plot my answer onto the plot that I just made, and we'll run that. And I guess that's kind of annoying because I made a separate plot, but if I run that, now it'll put it on there. Okay, there's the answer. Okay, and the great thing about solving nonlinear equations, similar to solving linear equations, is that if you think you have an answer, you can check it. I'm in my residual form. All I have to do is call the function on the thing I think is the solution, and if it comes out to be small like this, near machine precision, then I have the right answer. Okay, so I want you to practice okay, try some different initial guesses to find the other root. And try and type this out for yourself, okay? Don't just copy and paste. Try and practice that so that you have a chance to figure out on your own. I give you the answer here, but now would be a good time to pause the video and practice that on your own, okay? Once you've done that, now you can come down here and look at this final example that I have here, which is one of a system of nonlinear equations. Okay, so in this system, I sort of outline our generic form, and I say some of the things that I said on the previous paper, but you can go ahead and read through that on your own time in this example. And so what are the steps to solving this problem? It's the same steps as before. I have to import the module, put the equation in residual form. But this is now a little bit harder, right, when it's a system of equations. It's not that much harder, but it's a little bit harder than it is when it's just a single equation. And then I have to define my Python function as a vector function, okay? And this, if you'll notice down here, this is exactly what we were talking about earlier. We'll go over that a little bit in detail as we come down here, but just that's what's different, is the residual form and the Python function. Then we're going to set an initial guess. Notice that this guess is now going to be a vector. It's not just a single equation. It's one value for each number, okay, for each unknown. And then I'm going to call opt.root again with the same form, the function name, and the guess.x at the end. Okay, so for this example, we're going to solve y plus 2z equals 0, and sine of y divided by z is equal to 0. So the first thing is write that in our standard notation. They're already moved over to one side for us, but I'm going to rewrite the y's and z's as x0s and x1s to help me compare as I get down here. And I recommend that you do that on this homework that's coming up so that you can get comfortable converting it to vector notation. You don't have to, but I recommend that you do so that you don't get confused. Okay? So I'm going to take here, I'm going to define my function, def f of x. I use a big F here for whatever reason. And I'm going to call f0 equal to the first equation here, which is x component 0 plus 2 times x component 1. All right, and then down here I have my second function, f1, and I call that numpy.sine x component 0 divided by x component 1. Okay, so I define both of my equations, and then I return an array, numpy.array, which has f0 and f1 in it. All right, so now I can go down and define my guess. Note that my guess here, this is to x0, okay, that's my guess for x0, which is my guess for y, and this here is my guess for x1, which is my guess for z. And so when I call root, I call opt.root, my function name, okay, and then the value of my guess, .x, okay? And I go ahead and we can run that one. And again, I print example 2, I print yz, okay? Y is going to be the value of, the first one is x0, z is the second one, okay? So I get root there, all right? And I print the residual to check my answer, and I get 0 and minus 10 to the minus 15, something times 10 to the minus 15. All right, so I know that I've converged. Okay, so that's how you solve systems of nonlinear equations using scipy's root function. I have another practice if you have that would be good to do. So come down here, try and figure this one out. This one has 3 equations, 3 unknowns, x, y, and z. All right, and I tell you a reasonable guess to start with because it was a little bit trickier to figure that one out. Otherwise, it might not converge. And tell you the answers so you can know that you got it right. But you should be able to check that anyway with the residual, right? Okay, so that's all I have for the video. I hope this was helpful and wish you the best in all of your solutions to nonlinear equations.